Level 4.6 is focused basically on complex zeros and then the fundamental theorem of algebra. Before we talk about the fundamental theorem of algebra, we need a quick refresher on complex numbers. So I know you guys saw these last year, but just in case you forgot, complex numbers are numbers written in the form a plus bi, where a is the real part and b is the imaginary part. So complex numbers is a overall system that includes both real and imaginary. And oftentimes, I know we did set notation before with real numbers. This bold-faced Z is for complex. And if we wanted to write this in set notation, it's the reals and the imaginary numbers. That's how you write real, that's how you write imaginary. So if we put those two together, you get complex. So why do we get complex numbers and where do imaginary numbers come from? Well, I know I kind of hinted this at level 4.5, when we get the square root of a negative number. And mathematicians basically came to this problem before. They're like, okay, well, we set up these rules that the square root of negative numbers are impossible. But that happens frequently. So in order to solve these, we're just going to make up a number. So we're going to say that the square root of a negative 1 is I. And that's what they just came up with a notation. And from that notation, they built a whole new number system based around I. And so what we want to know is, so this is I to the first. If we know I to the second, that's just the square root of negative 1 squared. So that's negative 1. So that's what's going to be super helpful for us when we're factoring. And then likewise, I cubed is the square root of negative 1 to the third power. So that's a negative square root of negative 1, or negative I. And I to the fourth, which is square root of negative 1 to the fourth power, which is just 1. So these go in this circle from I to the squared, I cubed, I to the fourth. So I could ask you something like, what is I to the 250th power? And all you have to do is divide 250 by 4. And you see that, okay, that would be remainder 10, so which would be remainder 2 if you did this division, because all we care about is the remainder. 250 over 4 is something remainder 2. So that would be equal to negative 1. So we're definitely going to have a question on that in both our homework and on the test. So just know that various powers of I give you one of these four options. Either I, negative 1, negative I, or 1. So now we get to the big deal, the fundamental theorem of algebra. I even put 2 exclamation points after it. This states, I'll just read it, every polynomial function f of x of degree n greater than or equal to 1, so that means if our degree is bigger than 1, then that polynomial has at least one complex zero. Or another way of saying that, any polynomial of degree n has n roots, which is kind of what we were talking about before, but this caveat comes into place, says, but we may need to use complex numbers. So what does this mean and why is it important? So this means every polynomial is factorable and it can be reduced down to linear pairs or irreducible quadratics. So a linear pair is something like x minus c. And then an irreducible quadratic is something that's not factorable. And if something's not factorable, it either has irrational numbers, so we use the quadratic formula, or it gives us complex zeros. Okay, so then the next bit, conjugate pairs, which should sound familiar from last year, and complex roots. So let's say that these numbers are R1, R2, etc., may be real or complex numbers, but what we find out, and this goes back to something we've been hinting at for a while, is complex roots always come in pairs. So whenever you're given one complex root, you get another one for free, because in all of the polynomials, you'll never see I written out. And so in order to get rid of I, we write it as a conjugate pair. So you may be saying, well, you keep saying this word, conjugate pair. What does that mean? Well, we've been seeing this before. Let's say we had x squared minus 4. When you factor that, that's x plus 2 and x minus 2. These are conjugate pairs. And what that means is they are the same sign, same number, opposite sign. And what happens when we have conjugate pairs is when we FOIL this out, that's x squared minus 2x plus 2x minus 4, those middle terms drop off, which we are just left with x squared minus 4, what we started with. So this is going to be super important when we start talking about complex roots and we have imaginary numbers. So let's flip it and try a couple of problems like these. So example 1 is asking us, just write the conjugate pair, which I'm saying, just write this as an opposite. So what we do for imaginary roots to write conjugate pairs is we change the sign on the imaginary part. So the conjugate pair for 5i is negative 5i. The conjugate pair for 4 minus 2i is 4 plus 2i. The sign on the 4 doesn't change, the 2i does. For c, the conjugate pair is negative 5 minus 4i. And d, the conjugate pair is 3i. So that's just writing what, if I give you a 0, what is its conjugate pair? Okay? If we take that one step further and we start talking about conjugate pair of each complex root, and when we say root, root is the same thing as saying factor, which is the same thing as saying, well, we've been kind of hinting at zeros. So zeros can be written as roots or factors. Okay? So if we take the same as above, write the conjugate pair of each complex root. So first, let's write it as a root or a factor. So that would be x minus 5i. So then its conjugate pair would be x plus 5i as a root. Okay? How about b? If we write this as a factor, that would be x minus 4 plus 2i, because we changed the signs. So then the conjugate pair would be x minus 4. This stays the same, and then the imaginary part alternates. How about c? So this would be x plus 5 minus 4i, because we changed the signs. So then the complex root would be x plus 5 stays the same, plus 4i. So they alternate when we get down to here. And d, this would be x, there's no real part, just only imaginary, so plus 3i. And then the conjugate pair of d is x minus 3i. So this is writing complex roots out. So we either get no complex roots, or 2 complex roots, or 4 complex roots, or etc. We always have an even number of complex roots in a polynomial. Why is that? Because complex roots always come in pairs. So you will never have one I, or 3 things that have I in it, or 5 things that would have I in it. So we always have pairs of complex roots. So that means if we have degree 1, then we have one real root or factor or 0. If we have 2, that means we either have 2 real roots or we could have 2 complex roots. So that's our 2 real or 0 real and 2 complex. 3, that means we have, if the degree is 3, then we have 3 roots. So that means we either have 3 real roots or 1 real root and 2 complex. If we have 4, then we could have 4 real roots or 2 real roots and 2 complex, or just 4 complex. If this starts sounding familiar, it's just Descartes' rule of signs. So why we always drop the degree down, or why we said it's 5 or 3 or 1, is because we were taking into consideration complex roots without actually addressing complex roots to begin with. So if we have an odd degree, that means we're guaranteed to have at least 1 real root. Always. So one thing will work, and then possibly you won't be able to factor anything else. So then this corollary, which is kind of important, a corollary means it's kind of an addendum to a theorem, says every polynomial function with real coefficients can be uniquely, which means it's its own thing, factored over the real numbers into products of linear factors or irreducible quadratics. So we always want to simplify down to a quadratic, and then we'll see if we can factor that or not. That's what we said on the front page. And why is this so important? Because everything can be factored. Into linear factors or irreducible quadratics. So you could have 3 irreducible quadratics and you get a degree 6. That just means you have 6 complex roots. But everything can be factored, which is super important for us when we're talking about pre-calculus as a subject. Okay, let's flip it over and let's try a couple. So example 3, we're going to be assembling different polynomials, and then we're going to expand it all out. So we have to do a little algebra. So this says, for a polynomial of degree 5 whose coefficients are real numbers and has zeros 1, 5i, and 1 plus I. Find the remaining zeros. So our zeros so far are 1, 5i. Well, from the start, we said that complex zeros come in pairs, so we get negative 5i for free. Then we have 1 plus I as a 0. So that means 1 minus I we get for free. So negative 5i and 1 minus I give us our missing 2 zeros. And we have 1, 2, 3, 4, 5 roots or zeros. So then our degree is 5. Let's write these out as factors. So if 1 is a 0, then x minus 1 is our factor. 5i would be x minus 5i, then x plus 5i, then x minus 1 minus I, and x minus 1 plus I. Now it's asking us, write out all the factors of the polynomial. Okay. So x minus 1, x minus 5i, x plus 5i, x minus 1 minus I, x minus 1 plus I. I know it's not asking us this, but I want us to be able to do it. I want you to multiply this out. So get some practice. So currently I'm going to leave this x minus 1 together. If I FOIL this out, I get x squared minus 5ix plus 5ix, which the middle terms cancel out. So then I'm only left with squaring the last term. So that would be minus 25i squared. Okay. In here, I would have x squared, and then I have negative 1 negative 1x, and then I have plus ix. And then the next term, I'd have negative 1x minus plus 1, and then negative 1 times I, which would be negative I. And then I have negative ix, so I have negative ix. Negative would be plus 1I, and negative times a negative would be negative I squared. So I want you to see what happens here. The negative 1x, if I go down the line, negative 1x and negative 1x. So that would be x squared minus 2x. The ix, negative ix cancel out. The 1 stays, and then negative I plus I, those cancel, and you're left with negative I squared. And then I should have wrote plus 1. Okay, so this is like completing the square, or sorry, not completing the square, but a perfect square trinomial plus an additional I term. Now, from the start we said I squared was negative 1, so what that does is change the sign. And that's just 1, and that's just 1. So this fully factored out would be, and I'm just going to use one line here, it'd be x minus 1 times x squared plus 25 times x squared minus 2x plus 2. So that's that, at least without any imaginary pieces. And that's what I want you guys to be able to do. Okay, so I'm going to draw a little squiggly, and let's try B. Find a polynomial of degree 4 whose coefficients are real numbers that has zeros 1, 1, and negative 4 plus I. Well, that means negative 4 minus I is also a 0 because complex zeros come in pairs, and they come in conjugate pairs. So then if I wrote this all out, x minus 1, x minus 1, x minus 4 plus I, x minus 4 minus I. So then if I truly wanted to multiply this out, that would be x squared minus 2x plus 1. And here we would have x squared minus 8x plus 16 minus I squared. Well, this I squared is just a negative 1, so that changes that to plus 1. So then I have x squared minus 2x plus 1 times x squared minus 8x plus 17. Well, now you just have two polynomials. You can multiply these. So if I did this all out, x squared times x squared gives me x to the 4th. X squared times negative 8x gives me negative 8x cubed. X squared times 17 is plus 17x squared. Negative 2x times negative x squared is negative 2x cubed. Negative 2x times negative 8 is positive 16x squared. Negative 2x times 17 is negative 34x. And then 1 is plus x squared. 1 times negative 8x is negative 8x. And 1 times 17 is 17. So if I added all of this together, and I kept that on the screen, then you'd have x to the 4th minus 10x cubed. 17 is 34x squared. That would be negative 42x plus 17. This is a fully multiplied out polynomial whose zeros are all 4 of these. So example 4, find the complex zeros of the polynomial function. When it's asking for the complex zeros, that's saying find all zeros, both real and imaginary. Okay, so how do we do this? Well, that goes back to, okay, how many sign changes? There's one sign change, so there is one positive 0. If I switch these, I have 1, 2, 3, 3, 1, negative zeros. Okay, so that helps. And then I have a total number of 4. Now I'm going to list out my P's and Q's. So plus or minus factors of 18, which is 1, 2, 3, 6, 9, and 18, all over 1 and 3. So my entire list will be plus or minus 1, 2, 3, 6, 9, 18, 1/3, 2/3, 3/3 is 1, 6/3 is 2, 9/3 is 3, 18/3 is 6. Okay, so this is my list. I want to pick numbers that work, and just to expedite this process, I'm going to say, let's try, I would generally start with 1. I know I could potentially have, I know I have one positive 0, and I have at least one negative 0. So let's try negative 2. If I try negative 2 here, I get 3, 5, 25, 45, negative 18. Let's bring down the 3. Negative 6, that would be negative 1. That would be 2. That would be 27. Okay, these numbers will get pretty big. That would be negative 54. Okay, that works. So that would be negative 9, which would be 18, which gives me 0. Okay, so I just reduced that down by 1. The next one that I want to try, and this is just for me because I think there's a 3 out of here and I want to get rid of it, I'm going to try positive 1/3. So positive 1/3, bring down the 3, times 1/3 gives me 1. Okay, so that's 0, 0, 27. This looks promising. That gives you 9, which gives you 0. All right, and as we said before, it's asking us to find the complex zeros. So far, x equals negative 2 works, x equals 1/3 works, and the factors of that is x plus 2, and that would be x minus 1/3. So then this is now 3x squared plus 27, and we're setting that equal to 0. So we can divide everything through by 3. We're left with x squared plus 9 equals 0. Now here's the trick. X squared equals a negative 9. We take the square root both sides. Because we're taking the square root of a negative number, that would be x equals plus or minus 3i. Square root of 9 is 3. Square root of negative 1 is I. So then x equals plus or minus 3i, which means my factors would be x plus 3i, x minus 3i. So if I wrote those all together, I know it's not asking you, but just for our sake, this fully factored out is x plus 2, x minus 1/3, x plus 3i, x minus 3i. Factors, and then these right here, where we have x equals, these are our zeros. Those are our solutions. All right, flip it over. We've got one more to do. All right, last problem. So example 4b says find the complex zeros. So just like the last problem, what we want to do is like what we normally do. So sign changes, we'll count. We have one sign change, so one positive 0. If I switch these, I'll have 1, 2, 3. So 3 or 1 negative zeros, a max of 4. Okay. Now we want to do our p's over q's. So the numbers that multiply to be 75, so plus or minus 1, 2 doesn't go in, 3 and 25. So let's write these 3 and 25, 1 and 75. 4, nope, 5 and, let's see, 12, 13, 14, 15. So 5 and 15. And I believe 6, no, 7, no, 8, no, 9, no, 10, no, 11, 12, 13, 14, 15. All right, all over 1. So our list is plus or minus 1, 3, 5, 15, 25, 75. So those are the numbers that I want to try. I'm just going to start with 1. And for expedience sake, I believe this should work. So 1, 2, 22, 50, and negative 75. Bring down the 1. 1, 3, 3, 25, 25, 75, 75, 0. Okay, so I know that x minus 1 is one of my factors, and that takes care of my one positive. So I don't want to try any positives anymore. So I'm going to try negative 3. And using those numbers, bring down the 1, negative 3, 0, 0, 25, negative 75, 0. Perfect. So that means that x plus 3 is my factor. And sorry, these are my factors. I am left with 3 terms, so I stop. This is x squared plus 25. Now, if we're starting to see the pattern, this is not the difference of 2 squares, but the sum of 2 squares. And the way we factor the sum of 2 squares would be x plus 5i, x minus 5i. So then my 2 zeros are x equals plus or minus 5i. So this fully factored, and I'll write it in pink, is x minus 1, x plus 3, x plus 5i, x minus 5i. And that is finding the complex zeros. So what are the takeaways that you should have coming from 4.6? So complex roots come in conjugate pairs. I think that's super important. I think you should know the fundamental theorem of algebra, which says we can factor anything into complex roots. I think it's super important. We have now what I just showed you, the sum of 2 perfect squares, which would be, if it was x squared plus a squared, then that factors into x plus ai, x minus ai. And then to find complex roots, use the rational roots theorem, which is what we... So we're going to do what we normally do. And once you do that, once you get down to a quadratic, you can see if you can factor that quadratic. All right. This is going to be your next test. Good luck.